Hey guys, for calculus, this is from 3.4, and for pre-cal, when we learn cal at the end of the year, this is from 4.4. This lesson is called concavity. So this is the second time we're going to see one of the main applications of derivatives. Good news about today's lesson is that if you understood 2 videos ago the first derivative test, the second derivative test is identical, just doing all the procedures at the second derivative instead of the first derivative. So just to recap, the first derivative, doing setting it equal to 0, putting on a number line, checking the values in between, all of that told us about increase and decrease in the in-betweens, and then at the points it told us about max and mins, the extremas. So now we're going to do the exact same thing at the second derivative, and the in-betweens, when we test, instead of telling us increase and decrease, they will tell us about whether the function is concave up or concave down. And then the actual x values, instead of max and mins, these are going to be points of inflection, which a point of inflection is just a location where it indicates a switch in concavity. Okay? So let's go through this. Please, if you have not seen that video, make sure you go back and do so, okay? So step 1 is going to be to solve for the second derivative, okay? Just like last time, you're going to set that second derivative equal to 0 or undefined. And we're going to see an example today of that undefined. You're going to solve for x. Those x values on the second derivative are called possible points of inflection. And not to rewrite that long statement there so many times, we're going to put PPOI, okay? Points of inflections indicate a change in concavity. So if you look at this image right here, this dot where I switch from concave down to concave up is called the point of inflection, okay? Next, you're going to put those possible points of inflection on a number line, just like we did with the critical numbers, okay? You're going to test the numbers in between those possible points of inflection by plugging them into the second derivative, okay? If you get a positive number out, that indicates that you are concave up. If you get a negative out of the second derivative, then that indicates that you are concave down, okay? So now we're going to determine the actual points of inflection. Remember, we only had the possible ones up there. So if on that number line you find a switch between concave up and concave down, or vice versa, then you indeed have a point of inflection. If you stay from interval to interval, concave up or concave down, then you do not have a point of inflection, okay? And again here, in this, let's say you got whatever number this is here, let's say it was 2, as your possible point of inflection. When you tested before it, if the second derivative came out negative, that indicates that you are concave down on the function. And if you tested a number to the right of the 2 and plugged it into the second derivative and the value came out positive, that indicates that you are concave up on the right side of the 2 on the function. And because you have a switch, that value would indeed be a point of inflection. Okay? Now, to find out where that point of inflection is located, like how high or low to draw it, the same exact step happens from the first derivative test. You find the location of the point of inflection by plugging it into the original function, which would be back in the given. Okay? So we're going to do 3 full examples today. And for the sake of making everything connect, I'm going to go through the process of doing the first derivative test and the second derivative test so that you don't have to worry later about piecing it together. I want you from the beginning to know how all of this connects, okay? So let's go over how they start to connect with each other. Okay, I know there's a lot of writing here. Bear with me. If you find out that an interval is increasing and concave up, then this is concave up and increasing. Here we have it's increasing, but now it's concave down. Now we're left to right always. Always read math left to right. We're decreasing, but we're concave up. And here we're decreasing, but we're concave down. So for example, if I'm talking about this portion of a graph, I would have gotten out with my work that the first derivative was positive, which meant it was increasing, and that the second derivative was negative, which means that it was concave down. Okay? This portion here, I would have gotten that the first derivative was negative, which means it's decreasing, going downward, and that the second derivative was negative, that it was concave down. Okay? Here, I would have gotten first derivative negative, it's going down, it's decreasing. Second derivative is positive, it's concave up. Here, I would have gotten first derivative is positive. It's going up. It's increasing. And the second derivative is positive. It's concave up. And remember, the switches in increasing and decreasing are max and mins. And the switches in concavity are points of inflection. All right? So let's check out our first example. Okay? It says determine the points of inflection and concavity of f of x, which is x to the fourth minus 4x cubed. All right, so on this left side, I'm going to start off with the first derivative test. This is going to be more of a recap. All right, first derivative here is 4x cubed minus 12x squared. I can factor out a 4, and x's I can take out up to 2. And we're setting that derivative equal to 0, okay? So now I have 4x squared equals 0, and x minus 3 equals 0. X equals 0, and x equals 3. These are my critical numbers. I'm in my first derivative test. Okay? Now I put those critical numbers on a number line. Okay? We're going to put 0. We're going to put 3. There's no interval given. So now I need to test numbers in between. An easy number before 0 would be to plug in into the first derivative a -1. An easy number between 0 and 3 would be a +1. And an easy number bigger than 3 would be 4. Okay? So if I plug a negative number, remember it's always easiest in the factored one. No matter what number I plug in here, because it's squared, it will always end up being positive. And a positive times a positive is positive. So no matter which of these three numbers, this first bit here will always be positive. Okay? Now, if I put a -1 here, -1 minus 3, this does come out as negative. If I put 1 minus 3, also comes out negative. And then 4 minus 3, that comes out positive. Okay? So positive times negative is negative, which is going to indicate decreasing. -1 is before 0, so here I have negative and decreasing. Positive times negative is negative, which indicates decreasing. Okay? And positive times positive indicates positive, which is increasing. Okay? So far we can see decreasing to decreasing. I switched to increasing, so if I went down then up, that means here I have a min. Okay? And here I have none because there was no switch. So if I'm going to write myself a little bit of information here, I can say I was, let's do increase and decrease first. I could say I was decreasing from -infinity. Even though we still decreased here, I do want you to take the pause at 0 like they made you, okay? And then from 0 to 3. I was then increasing from 3 to infinity, okay? And the only extrema that I have is a min at my x value is 3. And then remember, I find the location of my min by plugging that 3 into the original question. Okay? So I have to say 3 to the 4th minus 4 times 3 cubed. Okay? You can go ahead and plug that in your calculator if you want. It gives you a -27. Okay? So this is all my information from my first derivative test. Okay? So now let's move on and do the second derivative test. Okay? Same exact thing, just at the second derivative, and we're going to label these names a little different. Okay? Second derivative test. Okay, so we're going to do the second derivative. We have the first right here. So f double prime of x is equal to 12x squared minus 24x. Okay, I can factor out a 12x, and I'd have x minus 2. And we're setting that equal to 0. Okay? Oops. So now set each equal to 0 because they're separated by multiplication. And now in my second derivative, when I solve for the x, these are called my possible points of inflection. Okay? I'm going to put those numbers on a number line. I have 0 and I have 2. Okay? Take critical numbers and possible points of inflection as, like, you know how you're in elementary you had like a word bank for your vocab test? Take these as like a number bank for what the answers could be, here for max and mins and here for points of inflections. So just because they come out here doesn't mean they'll end up being an extrema or a point of inflection. Okay? So now I'm going to test numbers in between, and because I'm on the second derivative, I'm going to plug them into the second derivative. On the first derivative test, I plug the numbers in between into the first derivative. So an easy number before 0 would be -1. An easy number between 0 and 2 would be 1. And an easy number after 2 would be 3. Okay, so we're on the new bit. This is review, first derivative test. New information today is second derivative test. So we are plugging it into the factored version. This is not squared, so I do have to be careful here. -1 times 12 is negative, times -1 minus 2 is also negative. Okay? Negative times negative is positive. Be careful, we're on the second derivative test, so this is telling me about concavity, not increase and decrease. A positive second derivative tells me it is concave up. Okay? So positive and concave up. Next, plug in 1. 1 times 12 is positive, times 1 minus 2 is negative. Positive times negative is negative. A negative second derivative tells me it is concave down. Okay? 3 times 12 is positive, times 3 minus 2 is a positive 1. Positive times positive gives me positive, so I'm concave up. And now, last time a switch told me a max or min. Here, a switch tells me an actual POI, an actual point of inflection, exists. I have 2 of them. Okay? So let's write my answers like we wrote this one. Let's talk about concavity first. We'll say concave up, concave down, and then we'll talk about the points of inflection. Okay? So I was concave up from -infinity to 0. Then I was concave down from 0 to 2. And then I went concave up again, so I'm going to add that to this list with a union, 2 to infinity. Okay? My points of inflection, I have 2 of them. I need to write these as ordered pairs. My first point of inflection happens at 0. And to find out the location of where it was, I need to plug that 0 back into my original. 0 to the 4th minus 4 times 0 cubed is 0. And my second point of inflection happens at 2. If I plug a 2 back into the original, 2 to the 4th minus 4 times 2 cubed, you can plug that in your calculator, and it gives you negative 16. And I am done with my second derivative test. This should feel like one of the easiest lessons to learn because you technically already learned it with the first derivative test. Just some new names, okay? So I'm going to get you a little head start on another lesson that happens in this chapter, and that's being able to draw it, which, believe it or not, is not too bad, okay? So what I want you to do is analyze what x values you're working with. Look at your number line. We have a 0 as the furthest to the left. We have a 2 and we have a 3. So we do want to show some space before the 0 to show the decreasing and concave up. And we do want to show space after the 3 to show that it is still indeed concave up and increasing, okay? So okay, I do have a min down here at negative 27. My points of inflection happen at 0 and negative 16, okay? So this is just a sketch, nothing too crazy, okay? So what I'm going to do is I'm just going to start marking not the intervals of concavity, but the max mins and points of inflection. So I have 0, 0 is a POI. And then I have 1, 2, negative 16 is a POI. So let's say negative 16. Again, this is a rough sketch. It's somewhere down here. And then I have a min at 3, negative 27. Let's say negative 27 is somewhere down here. Okay. And this is 1, 2, and 3. Again, a rough sketch. Okay. So before 0, if we look at our number lines, here's 0, I need to go decreasing and concave up. Okay, and if you need to refer back to this little chart that we drew here, decreasing and concave up should look something like this. Okay. So again, all of our graphs can look a little different as long as the behavior is correct. So I'm decreasing and concave up. Now after 0, I'm still going to be decreasing, but now I'm concave down up until 2. So I need to kind of change the curvature. Still decreasing, but concave down. So it kind of swoops here. Okay. Now after 2, I'm still decreasing until 3, but now I need to change concave up. Okay. So we see the POI here, right? The point of inflection. You can see that it changes from concave up to concave down. We can see the POI at 2, the point of inflection, because I went from concave down to concave up. And now I'm still concave up here, but I do change to increasing. Okay. And we can clearly see that 3 was our min. Okay. So again, as long as it looks similar and you see the concavities change and the increase and decrease change, you are doing a perfect sketch. Now on the AP test, they will not ask you to sketch any of these, but what they do very, very often is they give you the sketch and make you interpret the information. So I'm a firm believer in going forward and backwards is really going to help you get prepared for those kinds of questions, okay? Let's check out our second one. All right, here's our next question. Discuss the points of inflection and concavity of f of x. Okay, so I'm going to do the same exact process. If you feel confident, pause it and try it on your own as much as you can, and then check back in with me. So our first derivative test will be on the left again. We do our power rule. Okay, we can easily factor out here a 15 and an x squared. I personally like taking out the negatives just because I don't like them in the front. It's totally up to you. Here when I set each of them equal to 0, we get x equals 0. And then when I move the 1 over and I square root that, remember every square root, every even root has a plus or minus. So be careful there. We get 2 answers there. Okay, and these are my critical numbers because we're on the first derivative. So now I'm going to go ahead and put that on a number line. So we have -1, 0, and 1. Okay, so now we are checking 4 different spots. Okay, be careful with that. So an easy number before -1, plugging into the first derivative would be -2. An easy number between -1 and 0 is going to have to be -0.5. Same for after 0 and 1 would have to be a +0.5. And then after 1, let's say 2. By the way, a lot of times I have students ask me if there's a difference between when I'm writing capital or lowercase f's. I intend for all of my f's to look the same, guys, so don't worry about capital or lowercase. Those are just f's, okay? So now we're plugging these values into the factored version right here, okay? So no matter what I put in here, any of these numbers, positive or negative, the x squared is going to make them positive. And anytime I square anything, it turns positive. So positive times negative will always be negative for this first part, okay? All right, for this next part, now when I put the -2 here, -2 squared is 4. 4 minus 1 is a +3. Okay, negative times positive is negative, which would indicate decreasing. So I have negative decreasing. Now if I put a -0.5 in here, the squared makes it positive. 0.25 minus 1, again, positive 0.25 minus 1 would give me negative. Negative times negative is positive, which would indicate increasing. Okay. If I put a positive 0.5 squared, it still gives me a positive 0.25. Minus 1 gives me a negative again. Negative times negative is positive. I'm increasing still. Okay. And last one, if I put a 2 in here, 2 squared is 4. 4 minus 1 is a +3. Negative times positive is negative. I switch to decreasing. Okay. So we can clearly see here that I was going down and I switched to up. So I go minimum, decreasing to increasing. I stay increasing, and here I switch to go decreasing, which means I have a max. Okay. So let's write, it doesn't really matter what order you put this part in. Let's write our intervals of increasing, of decreasing, and at this point I do have a max and a min. Okay. So I was first decreasing from -infinity to -1. Then I'm increasing from -1 to 0. I'm going to take the pause because they had me do it. I continue increasing from 0 to 1. And then from 1 to infinity, I decrease again. Okay? Now, my max is at 1. And to find the y value, I need to plug that 1 into the original. Okay? So -3 times 1 to the 5th plus 5 times 1 to the 5th. And I get a +2. Okay? My min occurs at -1. To find the location, I need to plug that -1 into the original. -1 to the 5th stays negative because this is an odd exponent. So this becomes a +3. And then -1 cubed also stays negative. -1 times 5. We had a -5 and a +3. So we end up with -2. Okay. All right, let's go ahead and go for our second derivative test. Okay. So second derivative here, I end up with 4 times -15. I have -60 x cubed. And then I end up with 30 x to the first. Okay. So now I'm going to factor out a -30 again, just because I don't like that negative here, and a single x. So I end up with -30x, and then I'm left with 2x squared minus 1. Because they're separated by multiplication, I set each equal to 0. Here's one answer. And then here, I'm going to add the 1 over and divide the 2. So I have and now I really need to get that x by itself, so I need to do square root. Remember that every even root ends up with a plus or minus. So I know this looks like an ugly answer. I promise it won't be too bad. Okay, and these are my possible points of inflection. Okay, put them on a number line. I have a negative square root of 1/2. I have a 0, and I have a positive square root of 1/2. Okay, so now I'm going to pick some numbers in the in-betweens and before and after. I have 1, 2, 3, 4 different sections that I have to check, just like last time. And remember, I'm plugging these into the second derivative. So negative square root of 1/2, whenever I do a square root to like the number 4, it makes it smaller to 2. Whenever I do a square root to a fraction, it makes the fraction a bigger quantity. So 1/2 is like 0.5. Square root of 1/2 would go up to around like 0.7. You could always plug that in your calculator. So if this is like around negative 0.7, I could use -1 as a value to the left. Okay. And if I know that this made a 0.5 further, closer to 1, then I could use negative 0.5, I'm sorry, over here. Okay. And then I can use these same two numbers positive over here because I know that this value is the same as this one, just positive. So I'm going to plug in positive 0.5 and positive 1. Okay. Now I'm plugging these values into my factored version. Okay. -1 times -30 is going to give me a positive. -1 squared is going to be positive 1 times 2 is 2. 2 minus 1 is also positive. Okay. Positive times positive is positive, which indicates we're in concavity now. Concave up. Okay. Now, next portion, negative 0.5 times -30 makes a positive. Negative 0.5 squared, okay, is going to be that positive 0.7. Okay. And then times 2 minus 1 is negative. If at any point you feel like these numbers are crazy, guys, I do have a calculator in front of me, okay? Not for all of them, but like for these decimals and radicals, don't be afraid to use your calculator, okay? Just so you can double check where this is coming from. Positive times negative is negative. All right, negative indicates concave down. All right, now if I put 0.5 times negative 30, positive times negative is negative. Okay, and now 0.5, since the only thing that's changing here is that this is positive, but I'm putting it into a squared, and that squared made this one positive also. You're going to get the same number there, okay? So 0.5 squared times 2 minus 1 also gives me a negative. Negative and negative makes positive, which is concave up. And then 1 times negative 30 is negative. And then 1 squared times 2 minus 1 is going to be positive. All right, negative times positive is negative, which gives me concave down. Okay. All right, so on this one, we do have several POIs. We have a change here in concavity. We went concave down and concave up, so another one. And concave up to concave down. We have 3 points of inflection. Okay, so let's list our answer. All right, so concave up, I start here in this section. So I have negative infinity to negative square root of 1/2. Then I'm concave down from that negative square root of 1/2 up until 0. Then I'm concave up, so I'm going to list it here, from 0 to positive square root of 1/2. And then I'm concave down from that positive square root of 1/2 up until infinity. Okay? My POIs, I do have 3 of them. The first one happens at this negative square root of 1/2. We find the location by putting that into the original. Feel free to put that in your calculator. So that is 1.24. Okay. And then we also have one at 0. If you plug 0 into here, that one should be easy to do off the top of your head. You get 0. And lastly, we have one right here at positive square root of 1/2, which if you plug it into your original, feel free to use your calculator, you get, oh, I'm sorry, this one was negative. My mistake. This is the one that's positive 1.24. All right, guys? All right, so you've got all your info. Let's see what this looks like as a graph, okay? So the highest I'm going to go on max and min is to 2 and -2. And the lowest and highest I'm going to go for points of inflection is around 1 point something, positive and negative. So you don't have to draw your y's too high. And my x's, the furthest they go out to is positive and -1. So this isn't necessarily a really big graph. Let's use that information to draw our graph. Okay. So let's say I draw from 1 to 2, -1, -2, and then again the highest I go on my x values for max and min is also 2. I was a little lower. Okay. So now I'm going to just put a dot where my max, mins, and points of inflections are. I have a max at 1, 2. I have a min at -1, -2. Okay. And I have a point of inflection at -√1/2. If you put that in your calculator, it's about -0.7. And then at -1.24. So let's say this is -1. Let's say that dot lands somewhere around here. Okay. And then the other one is the same thing but positive. So positive 0.7 and positive 1.24. Let's say that's somewhere around here. And my third point of inflection was an easy one, 0, 0. So these three dots without labels are my points of inflection, and then I have my max and my min. Okay? So now let's look at my intervals. Looking over here. Before this 1 point, let's add it with a little red line. Let's say this was at -0.7 and positive 0.7. So before this -0.7, I should be concave up, and which should make sense with this being a minimum. But it says up until 1, I'm decreasing. So I'm concave up and decreasing. And then after 1, I am increasing, but I can only be concave up until this -0.7. Okay? Now, after that -1.7, I am concave down until 0, and I'm increasing until 0. So we should see some sort of a switch there, some curvature. Okay? After 0, I'm concave up, and after 0, I'm increasing. Okay? So concave up and increasing, it should stop at your next dot, which is this 0.7. Okay? Now, I'm going to have a max at 1, which means I'm still increasing to 1, but now, after this 0.7, I need to start being concave down. So concave down and increasing to max at 1. And then I'm still concave down, but now I just decrease forever after 1. Okay? So again, all of our graphs can look a little different, but as long as you are clearly seeing these changes in concavity and increase and decrease, then you are good. Let's do one last example. All right, so this question says, and it's our last one, discuss the points of inflection and concavity of f of x, which I'm giving you a fraction now. Okay, so this is the one where I told you we're going to see, you know how we set it equal to 0 or undefined? You should have learned back, it's probably in the back burner, that undefined means that you get a denominator of 0. Okay, so this is the example where we're going to see that. So let's start off with our first derivative test. F prime of x, I have low d high minus high d low over low squared. Okay? 0 times anything is 0. So we end up with 6 times 2 is 12, so I have negative, whoa, sorry, I was looking at the 6, negative 12x over x squared plus 3 squared. Okay? So whenever we say set derivatives equal to 0 or undefined, setting it equal to 0 in any fraction means that the numerator equals 0. A fraction being undefined means that the denominator equals 0. So when I tell you to set it equal to 0, what I'm really telling you to do is set the numerator equal to 0. And when I ask you to set it equal to undefined, it means set the denominator equal to 0. Okay, so one more time. If a fraction equals 0, it means the numerator equals 0. If a fraction is undefined, which, by the way, fractions are the only time you can really get undefined, the denominator has to get set equal to 0. Okay? All right, so let's keep moving. If I divide over the negative 12, here I get x equals 0. And then here, if I square root both sides, square root of 0 is still 0. So I end up with x squared plus 3 equals 0. X squared equals negative 3. X equals square root of a negative. Hopefully you remember that square root of a negative is an imaginary number. Okay? So imaginary numbers do not exist on a real graph. Therefore, we will not use this one. And my only critical number is 0. Okay? When we're working with functions, we're only working with a real number system. So if you ever get an imaginary number, just know it doesn't count as one, okay? So now, my only critical number is 0. I'm going to put this on a number line. And I'm going to test a value before and after 0 by plugging them into the first derivative. An easy number before is negative 1, and an easy number after 0 is positive 1. Okay? Here's my first derivative. Okay? You're going to hear me say very often that I want you to learn to think smarter and not work harder, okay? So anytime you have a denominator that the entire denominator is squared, no matter what I put into that x, positive, negative, big, or small, I'm going to square it at the end. If squaring is the last thing you do, it will always end up positive, okay? So as of now, you know that you are, for both scenarios, dividing by a positive. Dividing by a positive. Because again, no matter what number I put in here, this whole thing will end up positive. So now all I have to do is really analyze the numerator. Negative 12 times negative 1 is a positive. Positive divided by positive is positive, which means increasing for a first derivative. Okay? Now if I plug a positive 1 into here, negative 12 times positive 1 gives me a negative. And a negative divided by a positive, right, gives me a negative, which indicates decreasing for the first derivative. And I have found that because I switch from increasing to decreasing, I have a max at 0. Okay? Don't have any mins. So I was increasing from negative infinity to 0. And then I decreased from 0 on to positive infinity. And my max is located at 0. The way I find the location is by plugging my 0 into the original. Okay, which if I plug a 0 here, I'm left with 6 over 3, which equals 2. Done with my first derivative. Let's check out the second derivative test. Okay, so if this was my cleanest version of my first derivative, that's what I'm going to have to work off of. Okay, so I have low d high minus high. D low is a chain rule, be careful. Derivative of outside. Rewrite the inside. Times derivative, ooh, almost ran out of space there, of the inside. Okay? All over low, that's my low, and I need to square that. All right, this might take a minute to clean. Okay. But there's something I want to teach you to catch. And again, math isn't necessarily something that you can just stare at and boom, get the answer. It's kind of something you have to sit and analyze so that you can take the best option. So for example, the initial option you might think of is like, oh shoot, I have to FOIL all of that, then distribute the negative 12. And then here I have to do distribute, 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 and then I have to multiply those two exponents, okay? But, and this happens very, very often on the second derivative, you can catch that all three terms have something in common. So for example, Lodi high is one term, right? So all of this being multiplied is one term, minus Heidi low, all of this being multiplied is a second term, and then my denominator is its own term. So I'm going to underline according to term. Here's one term, here's a second term, and here's the third term. Okay? Again, this happens very often in the second derivative. If you can catch that there's an x squared plus 3 in all three terms, you want to analyze now how many can I take out? Well, this one has 2 of them, this one has 1 of them, and this one, 2 to the second power is to the 4th, so this has 4 of them, which means I could take 1 out of each. So I'm going to take this one completely out, which makes this multiplication way easier. Out of having 2 here, I can take 1 out, and now I'm going to have 1, which means now I don't have to FOIL. I can just distribute the 12. And out of having had 4 here, now I'm only going to have 3. Okay? So let's rewrite this. Now that I only have 1 here, I can multiply that negative 12 in. So I could say negative 12x squared minus 36. Now be very careful with this negative. I have a negative times a negative 12 makes a positive 12 times 2, positive 24, times another 2x is 48, and now I'm at x squared. So plus 48x squared. And this goes all over x squared plus 3 to the 3rd. All right, I know this is seeming crazy, but hopefully it just got a lot easier. Again, I caught that there was an x squared plus 3 in all three. I took 1 out of each, and then I was able to finish cleaning. Okay, so now I still have like terms that I can combine. So this is going to clean up to a negative 12x squared and a positive 48x squared is going to give me 36x squared minus 36 over x squared plus 3 cubed. Now that I cleaned my second derivative, okay, now I'm going to set this equal to 0 or undefined. Remember that setting equal to 0 means setting the numerator equal to 0. And setting equal to undefined means setting my denominator equal to 0. Now, because you technically have the same denominator when you do quotient rule, the exponent just went up once. This work is going to be identical to this one because cube rooting is 0 is still 0. So notice I'm at the same step here. So once you catch you're at the same step, you know that this is going to give you an imaginary number and you can stop. And again, we just worked smarter and didn't work harder. But in case you end up going through the motions, we'll write it out. And you'll start to see that the behavior of these questions are very repetitive. So maybe you don't catch it now, but maybe you'll start to catch it later, okay? And then here, 36x squared equals 36. X squared equals 1. And then when I square root 1, I get plus or minus 1. These are my possible points of inflection. Okay? Put them on a number line. I have 3 sections to check now that I'm plugging into my second derivative. I'll do negative 2. I'll do 0. And then I'll do positive 2. All right. So here's my cleanest version of my second derivative. Be careful because now my denominator is not an even exponent, which means this will not automatically be positive, okay? So let's check the numerator first. If I do a negative 2 squared, that gives me 4. 4 times 36 minus a 36, that's going to end up being positive. Divided by negative 2 squared, this is a 4. 4 plus 3 is going to be positive. A positive cubed is still positive. Okay? So this is a positive, which indicates concave up. Now a 0. If I plug in a 0 here, this cancels out and I'm left with negative 36. So I have negative divided by 0. This cancels out. 3 cubed would also give me positive. Negative divided by positive is negative, which means concave down in the second derivative. And last one, 2 squared. It's going to give me a positive 4 times 36 is a big number. Minus 36 is still going to be positive. And then 2 squared is 4 plus 3 is still positive, and a positive cubed is still positive. Positive divided by positive is positive, which yields to concave up. And because I can clearly see a switch, negative 1 and 1 are both points of inflection. Okay, let's make our list. So I was concave up on the 2 outside intervals, so from negative infinity to negative 1, and then from 1 to infinity. I was only concave down in between, so negative 1 to 1. And my point of inflection is at negative 1. I need to plug that into the original. Okay, so I end up with negative 1 squared is 1. Plus 3 is 4, so I have 6 over 4. All right, and then if I plug in my second point of inflection, 1, up here, I get 1 squared, which is 1, plus 3 is 4. I get 6 over 4 again. All right. Alrighty, let's use this information to draw, and then we are done for today. So notice that I only have a max at 2. I don't have a min. And then my points of inflection happen at positive numbers as well. So I'm going to draw this majority top. Okay. My max does happen at 0, 2. And then my points of inflections do happen at negative 1 and at positive 1. So, ooh, I drew that a little off. Let's pretend that looks closer. You know what? Let's fix it. Let's fix it. I'm sorry. All right, that looks a little better. So these 6 over 4s give you about 1.5. So I'm going to already draw my points of inflection at 1, 1.5, negative 1, 1.5, and then my max does happen up here at 2. Okay? So before negative 1, I'm concave up, and I'm always going to be increasing before 0. So first I'm concave up, and then I'm concave down. So concave up and increasing. I'm still increasing, but now I need to go to concave down. Right? I have my max at 0. I'm going to start decreasing, but I'm still concave down up until 1. And then after 1, I'm still decreasing, but I am concave up. Okay? And I'm done drawing it.